us forward in the individual areas, and we are in a focus area. They are technology drivers when it comes to filtration. Mann and Hummel has innovated a nanofilter technology for aluminium machining, and I don't want to go into the detail because our speaker will be doing this in a minute. Let us welcome Kai Becker, application engineer with Mann and Hummel GmbH. He will be talking about innovative nanofiber filter technology and a new mountain pleometry. Good morning and welcome. Right, good morning. Well, I've brought something along with me, as you see. I thought that it would make sense for you to sort of get what I'm talking about more precisely. I'm with Mann and Hummel, and I would like to show you two new filtration technologies.
Genau. So. Gehen wir hier auf die Folie zu Mann und Hummel. Also Mann und Hummel ist ein global agierender Filtrationshersteller. Die Firma wurde im Jahre 1941 durch Adolf Mann und Dr. Erich Hummel gegründet in Deutschland.
In Germany, that is, and we have 21,000, a bit over 21,000 employees worldwide. We have 80 locations distributed over 6 continents. In 2024, our sales were a bit over 4.5 billion.
Wir haben global 30
worldwide, we have 30 research and development locations and a bit more than 70 patents being filed every year, and we hope that one will be on this particular issue that I'm going to be talking about. And just so that you can estimate our production facilities when it comes to our global locations, we manufacture 30 filters per second. The area that I'm responsible for deals with industrial filtration, which includes trains and material handling, but also large engines and marine applications, just as the energy sector with filter applications for gas turbines and aviation and defense.
Raumfahrt. Und natürlich nicht zu vergessen, warum ich heute hier bin, für Werkzeugmaschinen.
Of course, also machine tools. And as you see at the bottom, we have a bit more than 73,000 individual product applications.
Wofür wir wahrscheinlich auch für jeden unserer Kunden eine passende Lösung
we have a suitable solution for each and every customer.
Ich selbst bin im Bereich der Manufacturing-Produkte.
So I work in the area of manufacturing products, which includes compressors, vacuum pumps, and the industrial liquid and air products.
Genau in dem Bereich bin ich auch tätig,
so
und
this
da
is where
möchte ich Ihnen heute unsere Filterprodukte vorstellen.
Particularly active in, and this is what I want to talk about today. On the left-hand side, on the right-hand side, rather, sorry, you see the filter that I've brought along. It's a filter for eroding applications. Then the centrifuge next to it that we offer as a product, particularly for large filter plants. Then there's a more compact solution, the filters in a housing for inline solutions, and it's all rounded off by the products for industrial air, oil mist separators, which are called scan mist,
auch als Elektrostarten angeboten werden. So, da möchte ich auch schon in das erste Thema starten.
Okay, that brings me to the first topic, the innovative nanofiber filter technology.
Dabei hatten wir das grundlegende Problem, mit dem auch die
So we had
Kunden
the
auf uns
basic
zugekommen
problem
sind,
that our customers approached us with. When eroding aluminium workpieces, there is a rather short service life and a low degree of separation with conventional medium of cellulose and synthetics.
Herausgefahren und bemerkt haben. Wir sind dann dazu übergegangen, zusammen mit der RWTH Aachen eine Untersuchung durchzuführen, warum denn diese Standzeiten
We tried to find out why these service lives were rather low in comparison to the filtration of steel particles. Well, machining speed, of course, is one essential factor because aluminium, due to its lower hardness, needs to be or can be machined more quickly. We have a factor of 3 for more dust generation. The other thing that was even more important was that the aluminium particles agglomerate very much more strongly, so that they form an aluminium sludge, which forms a compact filter cake on the medium. So we have a high differential pressure increase, and as we see in the image, the pleat is not covered completely in dust yet. And by increasing the filter medium surface in the microscopic area, by covering it with nanofiber on a cellulose carrier medium, we tried to solve this problem, or at least address it, and this is what I want to talk about now. So just to remind you what area of fiber sizes we're moving in, the human hair has about 50 to 100 micrometers, and from then on it starts with a cellulose fiber, via the synthetic fiber, and the very small dot on the right-hand side is the nanofiber, which has a diameter of 0.1 to 0.4 micrometers. What you see here is an REM image and the juxtaposition of the different media, the cellulose medium, which is comparably coarse and has rather open pores for rougher filtration purposes. This is an organic fiber. On the right-hand side next to it, there is a much bigger magnification. You see the synthetic fiber, which is inorganically produced. And on the far right, you see the nanofiber-coated medium, where the very fine nanofiber, which will not work as a medium in itself because it's very fine, it always needs to have some kind of carrier medium on which it can be applied. It would be a cellulose medium in this particular case. Just so that you understand the problem of filtration a bit better, I wanted to present the charge kinetics from depth to surface filtration and highlight what is important. So, basically, the filter medium needs to be used as well as possible. So more than 90% of our products use depth filtration, which means that the liquid with the dirt particles penetrates the medium, and the fibers depicted in green here then separate the particles into the liquid. Once that the depth is saturated, you go to the surface filtration part, and lots of particles collect and clog up the pores, which is what we call a filter cake. And later, this means that we have a rather quick differential pressure increase. Just to show you by way of an example where the differential pressure is when it comes to the dust or dirt penetration, where the depth filtration, we have a linear course, and once the saturation level, the clogging point has been reached, the surface filtration kicks in, where you have an exponential increase of the differential pressure via mass absorption. For our eroding machines and filter mediums, we call this, we use the surface filtration mechanism because the filter cake, which is collected, is involved in filtration. So you've got the filter medium, which has a certain degree of efficiency, and because of the collection of the first particles, the pores are compressed a little more so that even smaller particles can be separated. And in order to counteract this differential pressure increase, we have a lot more medium than in other products. What you see here is the product that I'm talking about, the nanofiber coated cellulose medium. We see the very massive structure of the carrier medium and only a very fine layer of a three-dimensional grid of polyamide nanofibers. And in the magnified image, you see that the pores that were originally in the cellulose medium are more finely distributed in the nanofiber. And that makes them more efficient. And this is how the process works. So the polyamide nanofiber is woven of a polymer reservoir, and due to van der Waals forces, there is a compounding process, and this brings about the product. During production, the woven or coated medium is continuously tested for consistence by the air measuring the air differential pressure. And by the nano coating, we have a good filtration efficiency so that the agglomerated aluminium particles are already in this three-dimensional structure of nanofibers, and that can be separated. In the microscopic area, you've got the filter medial surface, and we increase the dust absorption capacity of the medium and of the entire filter. This shows you the same cross-section through the filter medium. You see the different particles. The red points are the agglomerated aluminium particles that are only to be found in the uppermost nanofiber layer, whereas in the depth filtration, zinc and copper particles can also be seen, which come from the eroding wire made of brass. I'm coming to the central point, how to increase the service life of our filter and how to test this. We have service life surveys. We have a lab in Speyer where we have an eroding machine, and the filters are put in here and the aluminium is machined. And by cutting a rectangular identical part into the material 24/7, we measure the time until the filter has a differential pressure of 2.5 bar, which is then our basis of assessing how good a new filter product is in comparison to a standard filter product that we already have in our portfolio. And in the blue frame, you see the filter that was best up to now in our portfolio. It's got 14.8 square meters of filter surface and has a synthetic medium. And then on the right-hand side, in the orange frame, you see a higher filter, which of course has a bit more medium in it. And you see that the originally best filter only made it for 35 hours until the differential pressure reached the mark, whereas the other one in orange lasted twice as long. Of course, you've got to scale this down to the filter medium surface, and this is what we did in the left-hand side of the picture. So the synthetic medium has a service life of 2.4 hours per square meters, whereas the nanofiber coated cellulose medium has a service life of 3.8 hours per square meter. Those results are relatively recent, so we haven't had time to test the middle fiber filter, which corresponds to the one on the left-hand side in size. So we can only extrapolate the measurements here. But here we see that in a service life of about 50 hours, we still have a 50% improvement to the filter that used to be best in our portfolio. Then we have a turbidity measurement. That's a type of measurement where we find out how good the efficiency of the filter is. This is done online during the service life test in a light optical scan of the filtrated liquid. And what's particularly important here is that we only have a very short push of turbidity if you have the unloaded filter and insert it into the machine until the filter cake has collected, the efficiency of the filter products increases. So we only have a short peak in the beginning, which then goes down a little bit after 2 or 3 hours. So the synthetic filter goes to 10 NTU and has a continuous procedure, and the filter with nanofiber coating has more efficiency so that the NTU value doesn't increase all that much, even initially. Now, coming to the interpretation of the test results, with our tests we found out, of course, the filter was cut up, the filter medium was analyzed, and we found that the dirt from non-fiber coated media is very irregularly distributed with an irregular filter cake. So we have a high and fast increase of differential pressure, although there is still uncovered filter surface left, which brings us to the insight that for synthetic and uncoated filter media, the dirt absorption capacity, if there is a high dirt concentration, decreases over proportionally. For filter media, cellulose media with nanofiber coating, due to the increased filter media surface, in the inflow side, we have a better and homogeneous distribution of the dirt particles. Because of this, almost the entire pleat is used and covered in dirt, which brings us to the insight that the nanofiber coating, even if there are higher dirt concentration, leads to a higher specific dirt absorption capacity. Right, and this is the product overview. So we developed 2 products that you saw before. On the one hand, we have the low filter with 300 millimeters height, with a so-called kit for connections to Artishomi, Makino, Mitsubishi, Fano, and Sibu machines. And then, on the other hand, the bigger filter with more media, with more and longer service life, but with the same media, for the same machines. So, as far as the design allows, of course. And this is just a picture of our product flyers, which you can pick up at our booth. Right, now for the next topic, the new mountain pleat geometry. This is the filter that I've brought with me today to show you what this looks like, and I'll get back to that in a minute. Initially, we asked ourselves how to get an elephant into a fridge. Seems a bit childlike, probably, but it leads us to the question, how can you get as much medium as possible into the filter, into the housing, in order to ensure that the service life can be increased as much as possible? Because having more filter means having a better service life. But it's not only that. We also did tests with a filter housing with more than 20 square meters, and we didn't have such good service life because the second important factor is the pleat spacing. The liquid that is covered in dirt needs to move through the pleat as well as possible. And you see this in the diagram. There's a cutting point between maximum filtration surface and minimum pleat spacing. And there's an iterative process, and we think that with this new filter product, the so-called mountain pleat filter, is actually the optimum. As much filter as possible with a stable pleat spacing, which can be guaranteed by glue beads. So this is an excerpt from the mountain pleat filter. I think it's self-explanatory. You see that these pleats are folded progressively, and it looks a bit like a mountain, which is why it was called the mountain pleat. So what's special about this is that the pleats are rather stable, although the synthetic medium that's used is rather weak in comparison to the cellulose medium. And by optimizing the glue beads, by applying this next to every single pleat, we have a very stable structure, which is also stable in the filter, so that even if there are extreme applications, the differential pressures are as they should be. And that's really the core issue of this new development. Apart from the amount of medium, we concentrated on flow rates and on pleat spacings. So this shows you once again where we come from and where we want to go. The pleat structure, there was the conventional pleat technology, which is still in use with Mann and Hummel. These are rotative pleat bellows with pleat height that is always identical, which limits us with regard to media that fit into this kind of filter. And in the double bellows filter, this is increased by just having two bellows that have this pleat structure. Then we had the progressive pleat technology. And in the most simple case, the W pleat bellows, we have one small and one big bellows next to one another in order to ensure that there is more filter surface in the medium. And we had the triple bellows, and up until recently, it was the most highly performing filter in our portfolio. We had three massively pleated bellows, which were put into the same housing. And now we have this mountain pleat filter, which is the latest development, and I've just explained about that. So we see the different pleat technologies. We still have them in our portfolio, and the so-called mountain pleat filter is now almost in series production. So this is the development focus. I think I've summarized them all more or less. So basically, for our eroding machine, we wanted to have 20% longer service life in comparison to the triple bellows filter. And as I want to show you on the next slide, we actually managed to do that. So you've got the service life measurement once again with a steel workpiece in this particular case, and the cutting speed was smaller by the factor of 3 than in aluminium, which is why we have a very much longer service life. So looking at the diagram, up to a differential pressure of 2.5 bar for the triple bellows, customers, we had a service life of 150 hours, which is checked in many measurement procedures. And for Mountain Fleet, we could increase this to 180 hours. And what's remarkable about this is that in comparison, Mountain Fleet and 3 triple bellows, we have 20% more service life. And our customers have actually confirmed this. They've tried this out in real-life applications. Sometimes there even was a higher improvement. And once again, the turbidity measurement that we did, both filters have a comparable synthetic medium, so the measurements were relatively similar, with the NTU value that was rather high, as I mentioned before, initially, and then went down again. And here, once again, you see the product overview. We've got 2 variants of the filter with the Mountain Fleet structure, which we developed. On the one hand, we've got the kit option where the connection adapters for the machines are delivered for Makino, Mitsubishi, Fanuc, and Seibu. And we also have a SODIC option as a built-in cartridge. And we've already prepared the new flyers with good, better, best, or ultimate, which is the Mountain Fleet. And this brings me to the end of my presentation. And of course, I'd like to invite you to our booth, where we can talk about everything in detail, and where we can show you the different filter products. Thank you very much for your attention. Oh, right, yes, questions, if I may, of course. So, yes, it was a brilliant presentation. You said that the service life needs to be increased. What are scientific results about this? Of course, this filter concept, by the way, I just wanted to say it's really nice if, as a layman, you can actually understand what's going on. So, how much did this increase the service life? What is the economic effect? Answer, well, the measurement value was streamlined a little bit. We say 20%, and in real-life operation it's got to be confirmed, but a service life increase by 30% means that you need 1/3 less filters over the course of 1 year if you use the new filter. And the next question, talking about the economic factors, does the new filter cost more than the old filter? Because this has got to be mentioned. Well, unfortunately, I can't tell you that. But what I know from sales colleagues, I think that it's a comparable price level as for the triple bellows filter. How difficult is it to transform, over to the new filter technology? It's just plug and play, so it's the same size. That's why you asked how to get the elephant into the fridge. Of course, yes, the dimensions are exactly the same as before, and the size. I think initially you mentioned the different branches of industry, but what are the main areas of application? Of course, everybody can stand to benefit from this, but what are the main applications? Answer, well, it's EDM, it's the eroding area that's relevant because the purity of the liquid is relevant here. But in the meantime, it's also for coolants, lubricants, grinding machines, honing machines, and We have wires sometimes that are led through molds and rinsed by oils, where we can also come in with our filters. Now, you presented the mountain pleat technology, the new pleating technology. Will this be built into other filters too? Well, to tell you the truth, we haven't thought about that yet. What we want to do is to have a higher variant, just, to have an even bigger or longer service life. And we want to check in how far this can be done for other filters, because the design space is relatively high, and we don't know whether it's worthwhile having this pleat technology there. You did some experiments and have moved the product forward. Have you received feedback from users yet? Answer, yes. We are compiling it all, but we have 2 or 3 customers who've tested this already. And what's important to mention, by the way, particularly when it's GF, Chishami, or United Grinding, as they are now called, even for the new machine generation, these filters are in use. We are in very close connection with GF, and they were very enthusiastic about the new product and said that for the new generation of machines, our filters will be used. I thank you so much for the presentation, and